Hello, my dear student. Today I am going to start a new series, Pearson Edexcel International AS or A-level Physics, which is well known, as IAL Physics. Student Book 1. Writer Miles Hudson. Today we start from very beginning, working as a physicist. Working as a physicist. Throughout your study of physics, you will develop a knowledge and understanding of what it means to work scientifically. You will develop confidence in key scientific skills such as handling and controlling quantities and units and making estimates. You will also learn about the ways in which the scientific community functions and how society as a whole uses scientific ideas. And at the end each chapter in this book, there is a section called Thinking Bigger. These sections are based broadly on the content of the chapter just completed, but they will also draw on your previous learning from earlier in the course or from your previous studies and point towards future learning and less familiar context. The Thinking Bigger section will also help you to develop transferable skills. By working through this section, you will read real-life scientific writing in a variety of contexts and aimed at different audiences. Develop an understanding of how the professional scientific community functions. Learn to think critically about the nature of what you read. Understand the issues, problems, and challenges that you may be raised. Gain practice in communicating information and ideas in an appropriate scientific way. Apply your knowledge and understanding to unfamiliar context. Maths skill for physicists. We need some mathematical skill to perform IAL physics. Recognize and make use of appropriate units in calculations, such as knowing the difference between base and derived unit. Estimate results, such as example, estimating the speed of waves on the sea. Make order of magnitude calculations, estimating approximately what an answer should be before you start calculating, including using standard form. Use algebra to rearrange and solve equations, finding the landing point of a projectile. Recognize the importance of the straight line graph as an analysis tool for the verification and development of physical laws by experimentation. Choosing appropriate variables to plot to generate a straight line graph with experimental data. Determine the slope and interpret the linear graph. That means finding acceleration from a velocity time graph. Calculate the area under the line on the graph. Finding the average is stored in a stretched wire. Use geometry and trigonometry. Example, finding components of the vectors. Okay, this is the beginning of this section. Unit 1. Chapter 1 or topic 1, standard units in physics. In this section, first we have to learn about what is measurement, what is physical quantities. Let's start. Physical quantities and measurement. Lecture number 1. I am Jahangir Alam. I am a physics teacher. First, we have to learn about what is physics. The branch of science which deals with matter and energy is called physics. The main objective of physics are to establish the relation between matter and energy and to express it quantitatively on the basis of the observation, experimentation and analysis. Physical quantities are quantities that can be measured. Physical quantities can be represented by a symbol of quantity, numerical value for the magnitude of the quantity, the unit of measurement. So remember, to express a physical quantity, we need a symbol, a numerical value or magnitude of the quantity, and unit of measurement. Physical quantities. Anything that is measurable in the physical world is called physical quantity. So the things which we can measure in the physical world is called physical quantity. Are there anything which is not measurable? Yes. Emotion, honesty, patriotism, we cannot measure. That's why these are not physical quantity. So honesty is not a physical quantity. So anything that is measurable in the physical world is called physical quantity. There are two types of physical quantities, such as fundamental quantities and derived quantities. Fundamental quantity, the physical quantities which are independent or neutral, that is, they do not depend on other quantities, rather other quantities depend on them, are called fundamental quantities. Scientists have identified 7 fundamental quantities. These are length, number 1, 2 mass, time 3, 4 temperature, 5 electric current, 6 luminous intensity, and 7 amount of substance. Now, derived quantities. The quantities which depends on fundamental quantities or obtained from fundamental quantities are called derived quantities. As for example, velocity, acceleration, force, work, heat, electric current is the derived quantities. Derived quantities. Derived quantity is obtained by combining base quantities by multiplication, division, or both of these operations. Remember, look at the table here. Area. To measure the area, we need to measure length and breadth. Then by using this formula, length into breadth, we can calculate area. So area is a derived quantity. It is not a fundamental quantity. Again, velocity, look at the velocity. Velocity equal to displacement by time. Displacement one kind of length, so length divided by time. So velocity depends on length and time. That's why velocity is a derived quantity. Derived quantity. Unit of measurement. First, we have to learn about what is measurement. The act of measuring something in our daily life is called measurement. So the activities of measuring something in our daily life is called measurement. Unit of measurements. A standard is essential comparing with which any measurement is done. These standard quantities are called unit of measurement. There are 7 fundamental quantities and their units. Here, name of the quantities, symbol of the quantities, SI unit and symbol for the unit. First, number 1, length. Length is denoted by capital L or small l. Sometimes we use small l. Unit, meter, and symbol small m. Mass, sometimes we use small m and m for its symbol. SI unit is kilogram and symbol for the unit is kg. Third, time. Capital T or small t, both are used. SI unit is second and symbol for the unit is small s. Temperature, theta or capital T, SI unit is Kelvin and symbol for unit is K, Kelvin. Electric current I, SI unit ampere, symbol for unit capital A. Luminous intensity I or L, sometimes we use L. Unit, SI unit candela, short form CD. Amount of substance N, SI unit mole, 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 and symbol for the unit MOL. This chart shows the SI base unit and units: length, mass, time, electric current, temperature, amount of substance, luminous intensity. Here, a definition of meter, kilogram, second, ampere, Kelvin, mole, candela. This definition is very important for your conceptual concept of in physics. So, summary of this slide is: fundamental quantities are physical quantities that cannot be defined in terms of other physical quantities, for they have their own units. Derived quantities, quantities which are derived from fundamental quantities. So, standard units in physics. So, base quantity, unit name, and unit symbol. We have already learned about this. Standard units in physics. Uh, Sometimes the value we have to work with for some quantities, that mean the number involved are extremely large or small. For example, the average distance from the earth to sun measured in meters is 15,000,000,000,000,000 meter. So it is very difficult to understand. So scientists have made an easier system for writing such a large value by adding a prefix to the unit which tells us that it has been multiplied by a very large or very small amount. in the Earth orbit. Example, the distance is equivalent to 150 billion meters. The prefix giga means multiplied by a billion. So the Earth Sun distance becomes 150 gigameters or 150 GM. GM, capital G stand for gigameter. So 10 to the power 1 means deca, 10 to the power 2 means hecto, 10 to the power 3 means kilo, 10 to the power 6 means mega. Mega. The symbol for mega is capital M. 10 to the power 9 means giga, symbol capital G. And 10 to the power 12 tera, symbol capital T. 10 to the power 15 peta, denoted by capital P. 10 to the power 18 exa, denoted by capital E. 10 to the power 21 zeta, zeta, denoted by capital Z. 10 to the power 24 denoted by iota, 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 name iota, symbol Y. On the other hand, 10 to the power minus 11 deci, symbol small d, 10 to the power minus 2 centi, denoted by small c, 10 to the power minus 3 milli, 10 to the power minus 6 micro, denoted by mu, 10 to the power minus 9 denoted by nano, 10 to the power minus 12 pico, denoted by small p, 10 to the power minus 15 femto, denoted by small f, 10 to the power minus 18 auto, denoted by a, 10 to the power minus 21 jepto, denoted by small z, 10 to the power minus 24 iocto, denoted by small y. So these are very important for physics calculation. So look at the multiple and submultiple of units. So exa, peta, tera, giga, mega, kilo, hecto, deca. Deci, centi, milli, micro, nano, pico, femto, auto. So multiple and submultiple. Remember this thing. So base is 1, then 10 to the power 1, 10 to the power 1 means deca, 10 to the power 2 means hecto, 10 to the power 3 means kilo, 10 to the power 6 means mega, 10 to the power 9 means giga. On the other hand, 10 to the power minus 1 is deci, deci, 10 to the power minus 2 is centi, 10 to the power minus 3 milli, 10 to the power minus 6 micro, 10 to the power minus 9 nano, 10 to the power minus 12 pico, like this. Now, definition of dimension. Dimension of physical quantities means expressing them in terms of fundamental quantities by raising them to certain power. Dimension are always expressed in third bracket. Third bracket. So dimension of force. Say force equal to mass into acceleration. Again, mass, acceleration means velocity by time. Again, velocity means distance moved in a particular direction divided by time, and time 1 by time. So distance divided by time is squared. So dimension of the force is dimension of m is a dimension of mass is m here, dimension of mass m here. So and dimension of distance means dimension of length l, and a time inverse 2. So any physical quantities may be expressed as the product of one or more fundamental quantities of different powers. The power of the fundamental quantities in a physical quantity is called its dimension. So any physical quantities like force, work, energy, power. So any physical quantities may be expressed as the product of one or more fundamental quantities of different powers. The power of fundamental quantities in a physical quantity is called dimension. So dimension of power. Power equals to work done by time. So P equals to W by T. P equals to W by T. So dimension of work equals to L square M and T inverse square, and dimension of T is only T1. So power, dimension of power M L square per T cube. Like electric potential, we know electric potential means the amount of work done needed to carry a unit charge from one point to another point is known as electrical potential or voltage. V equals to W by Q. So W, dimension of W divided dimension of time. So we can easily calculate this dimension in this way. So why dimension is necessary? Uh, to check the correctness of the physical relation, to uh, re, what is dimensional analysis? Is the analysis of the relationship between different physical quantities by identifying their functional dimension such as length, mass and time. Limitation: dimension analysis cannot be used to derive the exact form of physical relation if the physical quantity depends upon more than three physical quantities. Try to check this one. Test the dimensional consistency of the following equation. Look, problem number 1, V equals to U plus AT. So left hand side, V is the velocity. So dimension of the velocity is L per T inverse. So dimension of the velocity. And right hand side U plus AT. Here U is the initial velocity, and A is the acceleration, and T for time. So dimension of velocity is L per T, and acceleration L per T square, inverse square, and time T. So L per T inverse and plus inverse. So 2 number or value is not important for dimensional check, consistency check. So left hand side equal to right hand side. So we can say this equation is correct according to the dimension. So that this is the way to find out the dimensional consistency of a physical relation or equation. Okay, sometimes we need derived unit like a force. The derived unit, the quantity derived quantity unit is Newton, symbol N, but base unit equivalent is force equal to mass into acceleration. So unit of mass is kg and unit of acceleration is meter per second square. That's why we can write so here a derived unit and base unit equivalent. Derived quantity force, unit name is Newton, and unit symbol is capital N. Base unit equivalent, because force, we know force equal to force equal to force equal to mass into acceleration. Here unit of mass is kg and unit of acceleration is meter per second square. That's why this is the base unit equivalent. So base unit equivalent of Newton. So Newton means kg meter per second square. Energy or work, unit joule, symbol capital J. So J equal to kg meter square per second square. How? Look at the work equal to force into distance moved along the direction of the force. So F into S. Here F means MA into S. So kg meter per second square. Then S means meter. So kg meter square per second square. Clear? Now power. Power unit name is watt and unit symbol is capital W. So watt W equal to kg meter square per S minus Q. So how? Power equals to work done divided by time. Work done means force into distance divided by T. And force means MA into S divided by T. M means kg, unit is kg, and meter per second square, and here another is meter, so divided by second. So kg meter square per second cube. So in this way we can find out the base unit equivalent. This is very important for IAL physics test. Very important for base unit equivalent. In physics, it can be very helpful to be able to make approximate estimate of value within an order of magnitude. This means that the power of 10 of your estimate is the same as the true value. For example, you are the same height as the ceiling in your classroom. If we consider the order of magnitude, the ceiling may be twice your height, but it would need to be 10 times bigger to reach the next order or magnitude. This is made clearer if we express all value in standard form and then compare the power of 10. You are likely to be 1,000 times smaller than an ant. So we would say you are 3 order of magnitude larger. So typically ant height is 1.7 millimeter. So 1.7 into 10 to the power minus 3 meter. Typical human height 1.7 meter. So 1.7 into 10 to the power 0 meter. So in many situations, physics are not interested in a specific answer. As circumstances can vary slightly and then a specific answer is incorrect. An order of magnitude answer will also be correct unless you change the initial condition by more than an order of magnitude. So physicists could easily answer the question, what is the fastest speed of the car? What is the fastest speed of the car? Because we don't really want to know the exact true value. To give an exact answer would depend on the knowing the model of the car, the weather and the road condition, and this answer would only be correct for that car on that day. By estimating important quantities like a typical mass of car, we can get an approximate order of magnitude answer. This reason for doing so would be it allows us to develop an ideas as possible or impossible. Also, it helps us to focus on the developing the idea along lines that will evaluate be feasible when we get developing scientific solution. This reduces the time and money wasted by following ideas that are impossible. It also helps us quickly notice any miscalculation in an answer to a question. So, size of the solar system 1 into 10 to the power 13 meter, 1 into 10 to the power 11 meter size of the earth orbit around the sun, 1 into 10 to the power 8 size of the moon's orbit around the earth, 1 into 10 to the power 4 diameter of the Manchester, 1 into 10 to the power 0 human height, 1 into 10 to the power minus 3 meter ant height, 1 into 10 to the power minus 5 meter biological cell diameter, 1 into 10 to the power minus 8 meter wavelength of ultraviolet light, 1 into 10 to the power minus 10 diameter of an atom, 1 into 10 to the power minus 14 diameter of an atomic radius. So estimation. Okay, now we'll discuss about measurement of length. Measurement of length. Avoiding reading errors. So parallax error, avoiding parallax error. When using the meter rule, the position your eye directly above the marking to avoid parallax error. So remember this thing. Parallax error occurs when we you we observe a reading from different angle. So when using the meter rule, the position your eye directly above the marking to avoid the parallax error. By taking several readings and taking the average, you will minimize the reading error. So accurate length 2.9 minus 1, so 1.9 centimeter. Inaccurate length of the object 3. Look at this diagram. Look at this diagram. If you did not check the reading avoiding parallax error, then you may get 3 centimeter minus 0.9 centimeter, so 2.1 centimeter. Measurement of length. Calipers, an instrument for the measuring the diameters of cylinders or circular object. Inverting the jaws of the calipers to measure the inner diameter. Internal calipers. Measuring length. External calipers. Calipers used to measure the outer diameter. Now Vernier calipers, a useful instrument to measure both internal and external diameters of the object. It consists of a main scale and a sliding Vernier scale. The Vernier calipers has a precision 0.01 centimeter. So measurement of the length, parts and uses the Vernier calipers. inside jaws used to measure the internal diameter of the object. There is a main scale and sliding vernier scale. A small sliding scale attached to the main scale. Attached to the This one is the vernier scale. This is the vernier scale. Uh, a small sliding scale attached to the main scale that allows us to read a fraction of the smallest interval. Outer jaw used to measure outer jaw. This one is the outer jaw. The outer jaws used to measure the external diameter or width of the object. Tail that used to measure the depth of an object, or probe. It is also known as probe. It is also known as probe. Measurement plane using a Vernier calipers. Before using the Vernier calipers, it is important to check the instrument for zero error. This is to check the zero mark on the main scale coincide with zero mark on the vernier scale when not measuring anything between the jaws. Table 1.4 Table 1.4 textbook shows how to deal with zero error. Read the main scale reading first. Read the main scale direct opposite the zero mark on the vernier scale. In this case, the reading of the main scale is 31 millimeter or 3.1 centimeter. 31 main scale reading. So main scale reading plus vernier scale coincide. Step 3, the fourth vernier mark coincide with marking on the main scale. This gives the reading the diameter of the fount. So vernier scale coincide into vernier constant. Here, main scale reading is 3.1 centimeter plus vernier coincide is 4, and vernier constant is 0.01 centimeter. So total reading is 3.14 centimeter. This is the way to measure spherical diameter of the spherical ball by using a Vernier calipers. Micrometer screw gauge. This instrument can measure the precision 0.01 millimeter. That means 0.001 centimeter. It is used to measure the diameter of wires or ball bearings. Step 1. Turn the thimble until the anvil and the spindle gently grip the object. Then turn the ratchet until it starts to click sound. Step 2. Read the main scale reading on the edge of the thimble. In this case, it is linear scale reading plus circular scale coincide into least count. This is a way to measure using a micrometer screw gauge. Reading on micrometer screw gauge. Micrometer screw gauge. So linear scale reading is 8.5 millimeter plus linear scale reading here, linear 8.5. So 5, 6, 7, 8, then 5. 8.5 millimeter, and 40 division is coincide with linear scale. So and vernier constant here 0.01 millimeter. So to exact reading here 8.90 millimeter. This is the reading here. Checking the checking and correcting the zero error when using the micrometer screw gauge. So this one is no zero error. Zero mark on the dotted line to the left, that means positive zero error. Zero mark on the dotted line in the right, so negative zero error. So key ideas: instrument with their range and precision. Meter rule, precision 0.1 centimeter or 1 millimeter. Example of uses: length of the to measure the length of the book. Measuring tape several meters, 0.1 centimeter and 1 millimeter, a person's waist. Vernier calipers 1 centimeter to 10 centimeter, and precision 0.01 centimeter or 0.1 millimeter. Diameter of the test tube. Example of uses: diameter of the test tube. Micrometer screw gauge less than 1 centimeter, that means 0.001 centimeter or 0.01 millimeter. It is used to measure the diameter of the wire. Error to take notes for each instrument: meter rule parallax error, vernier caliper zero error, and micrometer screw gauge also zero error. Voltmeter scale with a mirror mounted under the needle. So answer, figure 1.17 shows a voltmeter with a strip of mirror mounted under the needle and near the scale. Suggest how they may help to reduce the error when making reading. When taking a reading, ensure that your vision is placed directly above the needle so that the image of the needle coincide with the needle. This help to reduce the parallax error. Vernier calipers are used to measure the diameter of ball bearing. What is the reading of the vernier scale here? Main scale reading here 2.5 centimeter, 2.5 centimeter, and a vernier coincide third line. Vernier reading is 0.03 centimeter. So reading of the diameter will be 2.5 plus 0.03 centimeter, so 2.53 centimeter. The diameter of the wire is measured using a micrometer screw gauge. A student takes an initial reading and then reading of the diameter. What is the corrected diameter of the wire in millimeter? So zero reading here 0.02 millimeter plus, and diameter reading 3.87 millimeter. So corrected reading 3.87 minus 0.02, so 3.85 millimeter is the corrected reading. A simple pendulum consists of a bob attached to a string. A complete to and fro motion from R to S and back to the R is one complete oscillation. The time period T is taken for one complete revolution. A pendulum completes one full oscillation when the bob moves from R to S and back to the R again. All instruments use some kind of periodic motion to tell time. The mechanical watches or clock use the oscillation of string. Quartz was used the natural vibration of the crystals. Stopwatch can measure the time to precision 0.1 second. Digital stopwatch can show the reading 2 decimal places of a second. However, human reaction time introduces an error of about 0.3 to 0.5 second.